So in this case, when I want to find the complex roots or the real roots for a polynomial, the rule says that if I have a complex root is generally denoted in the form of a plus ib, where a and b are real numbers and I is a complex number which is root of minus I, is how we understand the complex number a plus ib. So if I have the roots in the form a plus ib where I is root minus 1, then always we say that complex roots appear in conjugacy, that is conjugate in pair. That is, when one of the root is a plus ib, obviously the other root must be a minus ib, which are called conjugate pairs. That is, I cannot have an instance where I can have a root as a plus ib, but a minus ib cannot be the root. A complex roots, if I have, as say I get 3 plus 2i as one of the root, then obviously the pair of 3 minus 2i should also be the root for a polynomial equation with real coefficients. This is how I understand the relation between the conjugate pairs of complex numbers. For a plus ib, a minus ib will also be the root, or if it is a minus ib, a plus ib will also be the root. This is how we understand the complex roots appearing in conjugate pairs. We call this as conjugate of this and this as conjugate of this. This is how we understand the conjugate pairs. So there are two important properties associated with the real factors or the complex factors, or the real roots or complex roots. To note with the two important points, firstly to start with, if p of x is a polynomial of degree n greater than 0 and a naught is its leading coefficient, then there are two important properties which are associated with this. If the leading coefficient is a naught and p of x equal to 0 is a polynomial equation of degree n greater than 0, then my first property says that if p of x equal to 0 has no real roots, then n is obviously said to be even, and not only that, f of alpha and a naught will have same sign for all alpha being the roots. So therefore, we need to understand the concept of n even or n odd to just cross check on the roots which we get. That is, when I find the roots of the polynomial function or the polynomial equation, if I don't get any real roots, then obviously I check that my n is even, because in that case of no real roots, my n must be odd. The degree n cannot be even, cannot be odd, but n, the degree of the polynomial equation, must be even. And not only that, further f of alpha and a naught will have same sign for all alpha. So if this is positive, this must be positive, or if a naught is negative, the f of alpha which you're getting as the root must be negative, is how we understand the concept of the first property. Now to start with the second property, which says that the case is with n odd. So when do we get the odd case? If n is odd, if my n is odd, then p of x equal to 0 has real roots, has at least one real root. Is how I understand the concept. That is, for n being odd, the polynomial equation p of x equal to 0 must have at least one real root. No real roots, n is even. At least one real root, n is odd. are the two basic properties which we identify in the roots of the polynomial equation. So let's see some problems which involves the roots which are complex in nature, and then finding the rest of the roots based on the complex nature of the properties. Now let's see an example problem where I take a polynomial function of degree 4 and I find the roots of that function. The question says if -1 plus root -1 is one of the root of x power 4 plus 4x cubed plus 5x squared plus 2x minus 2, then find the other roots is the question out here. Now, in case of these kind of problems, I use the properties of complex roots because clearly one of the root which is given is a complex root. So initially, to start with, let's take the given polynomial function into the equation. Consider the given polynomial function which is x power 4 plus 4x cubed plus 5x squared plus 2x minus 2 equal to 0. I take the polynomial equation in this form. Now, taking this as equation 1, I have one of the root alpha. It's given alpha is -1 plus root of -1 is one of the root for the given polynomial equation. Now, root -1 is I, so I can write this as -1 plus I, since I is root -1. He is one of the root for this polynomial equation. Now, using this, I had to find the rest of the roots. Therefore, identifying that the polynomial is of degree 4, there are basically 4 roots, and one of the root is given. I need to find the other 3 roots is the concept out here. Now, immediately when I have this as the complex root, its conjugate pair is also a root for this, as we have discussed in the previous session that complex roots always exist in conjugate pairs. So that implies the conjugate of alpha denoted by alpha bar, which is called conjugate of alpha, is nothing but -1 minus I, because wherever there's I replace that with minus I, is what I get, which is conjugate of alpha is also a root of equation 1, since by complex roots property, this is by complex root property that I have alpha bar or conjugate of alpha is also a root. Therefore, I have 2 roots which, that is -1 plus I, are the roots of p of x equal to 0. So I got 2 roots through which I'm going to find the remaining 2 roots. So when these 2 are the roots of p of x equal to 0, that implies I can write p of x as x minus -1 plus I and x minus -1 minus I times of q of x, because the degree of p of x is 4. So these 2 are the factors where the other 2 factors are given by q of x. So therefore, I need to find q of x in the next concept. Therefore, if I have this, if I take q of x on the left hand side and then put this on the right hand side, I get the quotient which I need to find here. So therefore, I get the 2 complex roots being conjugate to each other and then into q of x, because degree of p of x is 4 and degree of the conjugate pair is 2. Therefore, the degree of q of x obviously will be 2, which I'm going to find here. So before I do that, I just multiply this, because this is in the form of a plus b into a minus b, and then when I expand this, I get this to be x squared Therefore, I further simplified this so that I get this as x plus 1 minus I, and then x plus 1 minus I, and this is x plus 1 plus I of q of x when I expand the brackets. Now this is clearly in the form of a minus b into a plus b, where a is x plus 1 and b is I. Therefore, using the formula a plus b into a minus b, I get this as a squared minus b squared of q of x is what I get. Now this, on further simplification, gives me x plus 1 whole squared, which is a squared plus 2ab plus b squared minus I squared, which is minus 1, because I is root minus 1 and I squared is minus 1 is how I understand the concept. This times of q of x is what I get. Now this, on further expansion, gives me x squared plus 2x plus 1 plus 1 plus 2 of q of x is what I get for p of x. But because I want to find q of x, I take q of x to the left, and my p of x is already known to be x power 4 plus 4x cubed plus 5x squared plus 2x minus 2 times of x squared plus 2x plus 2. Now this p of x being the original function, this by this gives me q of x. Now when I divide this polynomial with this polynomial, the resultant I get is q of x. So let's see how I can divide the two polynomials. So when I take here x power 4 plus 4x cubed plus 5x squared plus 2x minus 2 with the polynomial x squared plus 2x plus 2, then I have initially x squared, which I multiply, I get x power 4 plus 2x cubed plus 2x squared is what I get. Then when I just subtract, I get this to be 4 minus 2 is 2x cubed plus 3x squared, carry forward 2x minus 2. Now again I need to multiply with 2x with x squared, so that I get 2x cubed plus 4x squared plus 4x, and then on subtraction I get minus x squared minus 2x minus 2. Now this, on subtraction of 1 and multiplied with this, gives me minus x squared minus 2x 0 as the remainder. That implies I have my q of x is equal to x squared plus 2x minus 1. Now I want to find the factors of q of x being a quadratic function. So when I use the factor form, I think it is not possible to do by factor form. So I use the formula x equals minus b plus or minus root of b squared minus 4ac by 2a, which on further simplification gives me minus this 4 plus 4, which is root 8 by 2. This is minus 1 plus or minus root 2 when I take 2 common and multiply. So I get 2 of the roots as minus 1 plus or minus root 2. Therefore, this will be with 2 possible factors. One is minus 1 plus root 2 and minus 1 minus root 2. So x minus 1 plus root 2 and x minus 1 minus root 2 is what I get for q of x. And therefore, I can find the factors using the whole of the polynomial. Has 4 factors. One is given by minus 1 plus I, minus 1 minus I, minus 1 plus root 2, minus 1 minus root 2. So this is how we find the 4 factors, the 4 roots of the given polynomial of degree 4 using only one of the given root, that is with one of the root as minus 1 plus I. I get one of the other root which is complex conjugate of this, and then we find q of x, and then we get finally the two roots. On the whole, there are four roots: minus 1 plus I, minus 1 minus I, minus 1 plus root 2, minus 1 minus root 2. Now we will see the transformation of equations, because sometimes when I transform the function f of x or p of x into another form, then the roots of p of x and the roots of the transformed equation definitely have some relation. So we are going to investigate on what are the possible relations we get when the different types of transformations are done for a polynomial equation, f of x equal to 0 or p of x equal to 0. So initially, to start with, the first property in the transformation, I see that when my f of x equal to 0 is transformed to, so this has been transformed into f of minus x equal to 0, then in that case, I say that if alpha 1, alpha 2, alpha 3, so on till alpha n are the roots of the function f of x equal to 0, then the corresponding roots of this would be minus alpha 1, minus alpha 2, so on and so forth till minus alpha n. So when I have the roots of the polynomial equation f of x equal to 0, I can find the roots of this transformed function or the polynomial equation without actually finding. Just with these roots, if I just change the sign, I get the roots of f of x minus x equal to 0. So the transformed function has its roots even transformed with change of sign respectively. So the roots and the transformed equations are definitely associated, as can be seen with this first property. Similarly, when I have the function f of x equal to 0, which is transformed to f of x by k equal to 0, then assuming the roots of f of x as alpha 1, alpha 2 till alpha n, the roots of this transformed function will directly be k alpha 1, k alpha 2, k alpha 3, so on and so forth till k alpha n, is how we understand the properties of the roots connected with the transformed functions. Similarly, let's see the next property of the transformed equations. So with the third type of transformation, say my function, my polynomial equation, this is transformed to f of x plus h equal to 0 with a quantity h added, then the roots of the function f of x equal to 0 assumed with this are transformed to alpha 1 minus h, alpha 2 minus h, alpha n minus h. So the roots are respectively transformed into this form. Is how we understand the third type of transformation. Next, we'll come with another transformation and see how the roots are connected. Now, let's take the fourth property where my polynomial equation, this is transformed to x power n times of f of 1 by x equal to 0. Then in this kind of transformation, we assume that the roots are non-zero, because when I have 1 by x form, the roots may go to the denominator. So assuming that each of alpha 1, alpha 2 till alpha n, where alpha I is not equal to 0, that is each of the roots is non-zero, or the roots of the polynomial function f of x equal to 0, then the roots of this function are nothing but 1 by alpha 1, 1 by alpha 2 till 1 by alpha n. Or if the roots have been 0 here, then the roots of this would have been 1 by 0. So therefore, if the roots of this have been 0, then the roots of this would have been 1 by 0 form, which is undefined. And therefore, the limitations are that the polynomial function f of x equal to 0 must have non-zero roots. Only then the roots of the transformed function x power n times f of 1 by x equal to 0 will have the roots as 1 by alpha 1, 1 by alpha 2 till 1 by alpha n, where n is the degree of the polynomial f of x. So n is the degree of f of x. So these are the four basic transformations we identify and the roots connected with the transformed functions. Transformation of equations connected with their respective roots. Now let's see some problems which are based on transformation of equations connected with their roots. So my example problem here says, find the polynomial equation or find the polynomial which has its roots translated by -3 for the polynomial p of x equals x square minus 5x plus 1 is what we get here. So therefore, here I identify that I had to find the polynomial of degree 2 in this case. Now in this problem, I have a translation done by -3 units. That is the polynomial p of x, which is given to be x square minus 5x plus 1. This polynomial is translated by -3 units where its roots are translated. Therefore, the roots of this being alpha 1 and alpha 2 are translated with -3 units. That is alpha 1 minus of this, alpha 2 of this. That is, I get alpha 1 plus 3. That is, this is being translated to p of x minus of -3 equal to 0 is how I get, because here h is -3. The translation is -3. So p of x minus h, because each of the root is translated with -3, so I get x minus of -3 equal to 0. Therefore, this on simplification gives p of x plus 3 equal to 0. And therefore, to find the polynomial which has its roots translated by -3 units for this polynomial is nothing but obtained when I replace x with x plus 3. Is how I understand the connection between the roots translated by -3 units and their equations also obtained through the translation as p of x plus 3 equal to 0 for p of x equal to 0. And therefore, when my p of x is x square minus 5x plus 1, p of x plus 3 is nothing but replaced with x as x plus 3 minus 5 times x plus 3 plus 1 equals 0. This on further simplification gives a square plus 2ab, that is 6x minus 5x, which is x, plus 9 plus 1, 10. 10 minus 15 is minus 5 equal to 0. Therefore, this is the polynomial function which has its roots translated by -3. Therefore, the required polynomial of the given problem is x squared plus x minus 5. I can take this as q of x is the required polynomial. So we can find the polynomials which are associated with translation of its roots in this manner. Now, the topic is about obtaining equations with certain missing terms. That is, if I give a polynomial and I wanted to delete sum of the power of x, say I want to remove the x power 4 term or x squared term or an x cubed term, I can do that and then find the new equation without disturbing the mathematical property of the equation. To understand this more clearly, let's try to enter with a live example. Now, to start with an example problem to support the topic, the question says, obtain the transformed equation of p of x equals x power 4 plus 8x cubed plus x minus 5 such that it has no cubic term, that is no x cube term. There is no x cube term is how we understand this problem. So basically I have an x cube term here which is 8, but the question desires that I have to transform this equation into a new equation without disturbing the mathematical property such that the new equation has no cubic term. So how do I do that is the biggest question out here. So in order to do that, I just proceed in the most simplest steps. Let p of x equal to 0 be transformed by h units. That is, I transform this equation by h units, then immediately I get p of x plus h equal to 0 because this is transformed by h units. Or say this is transformed or translated by minus h units, then p of x plus h is 0 is what I get. So this is translated by minus h units, I get this. Now as I know that p of x is x power 4 plus 8 times this minus 5, my p of x plus h is when I replace x with x plus h, that is x plus h whole power 4 plus 8x cubed plus 8x cubed, which is x plus h whole cube plus x plus h minus 5 equal to 0. Now in this I need to expand the powers of 4 and 3 using the binomial expansion. Now we know that the binomial expansion of this is x power 4 plus the next binomial coefficients of n equal to 4 are 1, 4, 6, 4, 1. We all know that. So for n equal to 4, the binomial coefficients are this. Therefore the first coefficient is 1, then 4, then 6, then 4 and 1. So I get next 4 times of x cube h plus 6 times x square h square plus 4 times x h cube plus 1 times h power 4 is what I get in my first binomial expansion. Now next, this is nothing but a plus b whole cube, which is directly a cube plus b cube plus 3a square b plus 3a b squared plus x plus h minus 5 equal to 0 is what I get in this entire expansion using the binomial expansion here and a plus b whole cube, and rest of them is same. Now the question here, if I read back, says that I have to transform the equation this into new equation such that it has no cubic term. Now if I want to delete the cubic term, I take into consideration all the cubic terms here, this, and that's it. There are no other cubic terms. So therefore coefficient of x cubed in the above equation is nothing but 4h plus 8, because if I take x cubed common, I get 4h plus 8 as the coefficient of x cubed, which I don't want in my new equation. So no cubic term. Therefore, if I just have coefficient of x cubed is 4h plus 8, no cubic term implies this must be equal to 0. That implies for the cubic term to be deleted from p of x plus h equal to 0, this must be equal to 0. I need to equate this equal to 0. So for the cubic term to be deleted from this, I have this to be 0, from which I get the value of h. Now 4h plus 8 equal to 0 implies h equals -2. So this is the value of h, which gives me the new transformed equation without a cubic term. That is, when I transform the polynomial equation p of x equal to 0 to -2 units, I get a new equation which has no cubic term. Therefore, that implies the transformed equation P of x plus h, that is P of x minus 2, has no cubic term, that is no x cube term. So this is how we understand the deleting or obtaining equations with certain missing terms, or deleting the terms as we desire. In this case, the x cube term is deleted. So therefore, let's see if we are correct with our expansion. So to find f of x, P of x minus 2 is nothing but taking this replaced with this plus 8 times x minus 2 minus 5. And therefore, when I expand, I get a new equation which has no x cube term. So let's expand and see if we have an x cube term missing out there. Therefore, this on expansion gives me P of x minus 2 on expanding this gives me x power 4 minus 24 x square, and then plus 65x, and then finally with the constant negative 55, which has no x cube term. As can be clearly seen, it has a term with degree 4, degree 2, degree 1 and 0, but it does not have x cube term. Is how we understand the concept of obtaining equations with the desired missing terms. Now the next topic is about reciprocal equation. So before we discuss about reciprocal equation, let's see what exactly is the definition of a reciprocal function. So to define the reciprocal function, I have the definition for reciprocal function as a polynomial. Say I take f of x of degree n greater than 0 is said to be a reciprocal polynomial if I have the condition f of x can be expressed in the form a naught by f of 0 into x power n of f of 1 over x, where f of 0 is not equal to 0 is the condition, of course, because if it is equal to 0, the denominator becomes 0 and hence undefined. The whole of f of x would become undefined. So the condition is f of 0 is not equal to 0 and a naught is the leading coefficient of f of x. Under this condition, I say f of x is a reciprocal polynomial, is how I define the reciprocal polynomial of degree n greater than 0. Now in this, when I talk of reciprocal equation, the reciprocal polynomial equated to 0 is called a reciprocal equation. So now that we have defined the reciprocal polynomial, if I take the reciprocal equation, reciprocal polynomial equated to 0 is called a reciprocal equation. Therefore, this when equated to f of x equals a naught by f of 0 x power n f of 1 over x equated to 0 is called a reciprocal equation, and this is called a reciprocal polynomial, is how I differentiate between the reciprocal equation and reciprocal polynomial. So this is the definition of reciprocal equation. Now here the condition is that this is for all, this must be equal to this, equal to 0 for all x belonging to the complex numbers minus the 0, or the complex numbers minus excluding 0 or here even this applies even for the reciprocal polynomial. When I say C over 0, it is understood that this indicates all complex numbers except the term 0 is how I understand the notation C oblique 0 or C minus 0. So this complex numbers does not include 0, but other than that it includes all the complex numbers which are non-zero. Is how I understand for all x belonging to. Now let's see some properties connecting the reciprocal equation with its respective roots. Now the reciprocal equation is classified into two types. One is class 1 type and class 2 type. So let's see what is class 1 reciprocal equation and class 2 reciprocal equation. So before that, I considered a polynomial equation, a reciprocal equation f of x equal to 0 with degree n greater than 0 and its leading coefficient being a0 and a0 being its leading coefficient. So if I wanted to identify this to be class 1 or class 2, for this I have two classifications which have their respective definitions. Class 1 and class 2 reciprocal equations, or class 1 functions or class 2 functions. Now in this case, we say that the function f of x is class 1 type if my f of 0 is exclusively the leading coefficient a0. That is, when I substitute x equal to 0, then f of 0 must be equal to a0. In this case, we call this as class 1. That implies f of x is a class, f of x equal to 0 is a class 1 equation, is how we identify here. Similarly, for class 2, I have, if my f of 0 is minus a0, that is minus of the leading coefficient of the function, then in this case I say f of x equal to 0 is a class 2 equation, is how we differentiate between the class 1 and class 2. F of 0 equal to a0, f of x equal to 0 is a class 1 equation. F of 0 is minus a0, then this is a class 2 equation, is how we understand the concept. Now let's see this through an example problem on how we can understand more better on class 1 and class 2 equations, and of course the reciprocal equation associated. To start with, an example problem which says, show that, the question is, show that the polynomial p of x equals 2x cubed plus 5x squared plus 5x plus 2 equal to 0 is a reciprocal equation of class 1. That is, I had to show that this given polynomial equation is a class 1 reciprocal equation. So in order to do that, first initially I take the polynomial equation which is given to be p of x equals 2x cubed plus 5x squared plus 5x plus 2 equal to 0. And I observe here that my degree n is clearly 3 because it is the highest power identified in the given polynomial equation. My degree is n and my leading coefficient a0 is a0, which is equal to 2. So these are the two basic things through which I identify the reciprocal equation, and of course its class 1 nature. So initially I want to show that this is a reciprocal equation. So how do I show that this is a reciprocal equation? By definition of reciprocal equation, I have that by definition of reciprocal equation, I have to identify that my p of x, if it is a0 by f of 0 of x power n f of 1 over x, then I say that my P, if I take here as P, then I say that P of x is a reciprocal equation if equated to 0. Therefore, let me just identify that this is a reciprocal polynomial. So in order to do that, I just try to simplify the right hand side, and I must get the left hand side as P of x, or this is P, it's not F. So in order to show that this is equal to P of x, I consider the right hand side and simplify, where my right hand side, which is a naught by f of 0 x power n of P1 over x is nothing but a naught, which is 2. Therefore, I get a naught as 2, and P of 0, which is P of 0, which is 0 plus 0 plus 0 plus 2. So therefore, when I substitute x equal to 0 in this, all the 3 vanish and I get 2 in the denominator. And this is nothing but P of 1 over x, which is nothing but 2 1 over x of cube, and 5 1 over x of square, plus 5 1 over x plus 2 is what I get. And I want to simplify this to show that this is again nothing but equal to P of x. So let's simplify this. So this on expansion gives me 2 by x cube plus 5 by x squared plus 5 by x plus 2 is what I get, which on further simplification through LCM of x cube, I get this to be simplified with 2 plus 5x plus 5x squared plus 2x cubed is what I get. Now this is nothing but I get in the form 2 plus 5x plus 5x squared plus 2x cubed. So rearranging each of the terms, I find that this entirely is equal to 1 by x cube of P of x is what is identified. Of course, I didn't take this x cube here. This is x cube which I get on the whole multiplied with x cube because x power n is missing, and then this one multiplied with x cube gets cancelled with the x cube, and so that I get P of x, which is nothing but proves that implies P of x is a reciprocal polynomial, and hence P of x is a reciprocal equation is what we identify. But how do we identify that it is of class 1 or class 2 type? So clearly I know that for finding for class 1, class of P of x, we try to take P of 0 and then we find the leading coefficient compared with P of 0. So when I put x equals 0, my P of 0 is 0 plus 0 plus 0 plus 2, which is 2. But this is clearly the leading coefficient a naught. Now when P naught is equal to a naught, that implies P of x equal to 0 is a class 1. Because of the definition, class 1 reciprocal equation is how we identify. Hence, we showed that this is a class 1 reciprocal equation. Is how we understand the reciprocal equation of class 1 and class 2 connected with the given polynomial.